Hello, Nick here, M0NTV, and welcome back to my shack and to part 3 of our Mixer Trilogy. And if you haven't seen the other 2 parts, by all means go and check those out. In part 1 I built a diode ring double balance mixer. In part 2 I built a Diplexer, which is going to house the IF port, and tested that. And finally, part 3, the long awaited testing special. And so this is where I'm going to put it all together and show you what it looks like with and without the Diplexer, so you can see the difference that it makes. And which raises a really important question that we better tackle right at the beginning here. How on earth are we going to test this mixer? And there are different ways of doing this. The first thing is to say, whichever way we choose, you are going to need some form of test gear, right? So you're going to need, first of all, a method of producing RF signals. So, because you're going to need to simulate your local oscillator and your RF signal coming in. Now, the easiest way of doing that is with a signal generator, and that's what I'm going to use. So I've just got a cheap Chinese SigGen, and you can homebrew your own. There are different ways. So that's what I'm going to be using for that. But the other thing is, we're going to need some way. Well, for me, this is just a personal preference. I need to see things to understand them. I want to be able to see those signals. So really, you want some way of representing your mixer output in the frequency domain, right? So you need some form of spectral apparatus, for want of a better word, to actually see this. Now, if you're lucky enough to have a spectrum analyzer, well, good for you. You know, your quid's in. I don't. Well, not a real one anyway. But don't worry, you don't need one. There are other ways that you can measure fairly reliably the output of your mixer, even if you don't have a spectrum analyzer. But there's different ways of doing it. So I'm going to show you 3 different ways. I'm going to spend the most time on the first one because it's easier to show you what's going on with the first one. But the other ways you can use as well. But before we get into that, we better just address the question of what are we actually looking for in the first instance. Okay, well, this is Mixers 101. And in truth, what's going to follow is a little bit of theory here, so that if this doesn't float your boat, then by all means feel free to skip it to the next more practical bit. But if you're interested in how it works and what you're going to be looking out for, then stay tuned. Right, okay, well, how does it work? Well, here's our mixer, and we're going to put into our mixer, one of our inputs is an RF signal. And obviously I'm building this for the 17 meter band. So let's imagine we've got an upper sideband signal lying between 18100 and 18103 kilohertz. Now I know that's a bit wide. You wouldn't normally perhaps have a 3 kilohertz signal, but just to keep the maths easy, let's imagine we've got a 3 kilohertz signal upper sideband going into the RF port. Now, the local oscillator is being driven at 31425 kilohertz. Now, a mixer, of course, 3-port device, 2 inputs, 1 output. Those signals will combine to give us our output, and we'll have 2 main outputs that we will be expecting. So one is the sum of those 2 frequencies. So I've got our waveform here. So the 18100 plus the local oscillator, and the upper end of the RF frequency, the 18103 plus the local oscillator, and so that will give us our waveform lying just south of the 6 meter band. But that's not what we're interested in. Of course, what we're interested in is the difference frequency. This is the RF minus the LO, which is going to form our intermediate frequency, our IF. So if you do the maths again, 18100 minus 31425 gives you minus 13,325 kilohertz. Hang on a minute, you say, how on earth can you have minus 13,325 kilohertz? Well, you can't, of course. Well, you can, mathematically, that's exactly what it is. But in reality, there's no such thing as minus 13,325 kilohertz. There's just 13,325 kilohertz. But that minus tells us something really important, which you'll see in just a moment. It tells us that our signal is inverted in the mixing process. So let me show you, because it's far easier, I think, to show you on a diagram than it is just to give you a bunch of numbers. So, okay, let's imagine this is our signal. This is our original RF signal, and it's lying there between 18100 and 18103. And you'll see I've represented it the way that the audio has been modulated, imagining that this is a real signal, has been modulated onto that RF signal. That is to say, the higher in frequency you go through the 17 meter band, the higher the frequency of the audio wave. In other words, it's not inverted. And that's a really important point. It's an upper sideband signal which is not inverted. If it was lower sideband, it would be inverted. But it's not. Okay, that's what we're putting in. Once we've mixed it to our IF frequency, what happens? Well, this. It is inverted, and that's what that minus figure tells us. It means that we indeed get our signal lying at 13,322 to 13,325, but it's now the wrong way round, we would say. That's not a problem, and I will just say, although it's technically not really part of this video, but when we go on to build a product detector later on, what we'll actually do is put in the signal lying there between 322 and 325. We'll put in a beat frequency oscillator or carrier insertion oscillator at 13,325, and what happens is when you do the maths again, you end up with an inverted signal that seems to lie at minus 3 kilohertz, which of course can't happen. But an incredible thing happens when you do this, when you get down to the DC mark, the naught there, because what happens is the signal folds around the DC mark, and you get this. Wait for this. 1, 2, 3, and it folds around, and lo and behold, it ends up the right way round. Yeah, the magic of RF mixing. So we'll be able to listen to that signal, and it won't sound like Donald Duck, which is great. So, so that's that. Now, what are we expecting to see? Well, it's a double balanced mixer which is supposed to attenuate and suppress both of the inputs, the RF and the local oscillator, leaving us just our expected outputs, the sum and the difference. So you'd expect that on some spectral display we would see this. There's our sum and there's our difference, but in truth we're going to see something more like this, and in actual fact it'll be a lot worse than that. There'll be lots more intermodulation products, lots of spurs and close-in harmonics and things in there, and it could be a lot more messy than that, but this is just the basics. Because I want you to see this, because in a minute when you're going to look at the screen, it's useful to have some kind of reference point in your mind about what you're supposed to be seeing. And I just pay particular attention. You'll see the RF there, which is knocked down a little bit, but it's the local oscillator which is the one that we're watching, because that's the strongest signal, and that's the one we really want to attenuate as much as possible and get as much difference in signal strength between our difference frequency, our IF, and our local oscillator, and that's the degree of suppression really of the LO. So that's what we're going to be looking at, but you will see other harmonics and things as well. Right, well, let's get practical. Okay, well, here is the original diode ring double balanced mixer. This is the one without the Diplexer, and because I thought it was useful actually, so I built one which is identical to the other one, but it was useful for testing purposes, but it has no Diplexer, and so I've got that connected up to my SIGGEN down here. Now if I can just get in here and just show you. So here's my SIGGEN, and hopefully you can see I've got channel 1 set to the local oscillator, that's 31425, 1.4 volts peak to peak, which is about 7 dBm, which is what you would usually think of driving these passive diode ring mixers with, and we'll play around that in a minute. And then channel 2 is simulating my RF, so 18100, and I've got that set to 170 millivolts. And what we're going to use is an oscilloscope. And you might think, I thought I said that we had to see it in the frequency domain. Well, yes, but it depends on your oscilloscope, because if you've got a more recent oscilloscope that's got an FFT, a fast Fourier transform function on it, then you can do something like this. So let's just come in here. Hang on, let's get that wire out of the way. So here is my my scope, and you can see. Let me just freeze it for a minute so it's a bit easier to see. Yeah. So, and you can see here why I wanted to show you what to expect first of all, otherwise it could be a bit confusing. Right, I'm going to try and hold this and point at the same time. This could be disastrous. So here, this is RIF frequency. This is the difference. Over here, this is the sum. This is the RF frequency. That's a harmonic. That's the local oscillator. That's what I've got it centered on, the 31.3. These figures, this is clearly not as accurate as anything like as a proper spectrum analyzer, but it gives you a rough idea. I pinched this idea shamelessly from Charlie Morris, ZL2 CTM, because that's how he tests his mixers, and it seems to work pretty well. That's under the spur. That's I think the image frequency there. So the ones we're looking at most are these two, and you'll see I've got the cursor set to this. I've got the E cursor, the top one, is set to the top of the IF, and I've got the S cursor set to the local oscillator. And I don't know what you can see down here actually, but it will show you. So here, at bottom right, 27.2 dB. So that's the separation between those cursors. So in effect, that's the amount of power that the local oscillator is being attenuated below the level of the IF. So 27 dB. So I mean, it's all right. I mean, it's, you know, I've seen a lot worse, but could be better. So that's what it is. Now, what you have to do, the thing is, with this mixer, we've only really got two parameters. We've got the drive of the local oscillator, and we've got the drive of the RF signal. So it's a question of playing around with those until you get the best of both worlds. Now I'm going to try and do this a little bit so you can see, but essentially if I was to crank up the power on the local oscillator, then you see everything's coming. You see all those other harmonics coming up there now, and you see actually that the level of the IF has not really gone up, but we've got a whole load more harmonics and noise. So that's clearly not the way to go. So I'm going to take it down again. But if I drop it, I'm back to 1.4 volts now. If I drop it too low, I'm going down now. Now you can see it. You can see that IF signal that on the left dropping down. So everything's dropping, but so's that. Now that's it's gone all together now. That's 500 millivolts peak to peak. I'm not surprised. Yeah. So actually, the 1.4 volts does seem about right, I have to say. Now, if you were to play around with the level of your RF signal, you might get a bit more joy with this. Now you can see I'm cranking up. Now the signal is going up there, so you probably could get a bit more out of it. It depends whether you're settling for those harmonics. I mean, it is going up quite a bit, so you could put more through it, you know, if you were amplifying in an IF amplifier or whatever.
but obviously you've still got all those other harmonics and things there, but you could filter those out. So you could probably put a bit more signal through it, no worries at all. I mean, that was just an arbitrary thing, that 170 millivolts, but you wouldn't really want to mess around with too much more local oscillator, I think is the message there. So it's one of these things you've got to play around with it and see. And the thing with home brewing your own mixer, then one is not going to be identical to the next, so it depends how you built it.
So some results. Now, instead of trying to hold the iPad up in front of the scope and getting loads of shaky camera work that's going to do your head in, I decided what would be easier would be to take some screen grabs of the scope, and it allows me to do that, and I can talk to those and show you them. It might just be a bit easier on the eye. So here we go. So this was pretty much what you've just seen. So this is the mixer, the old mixer alone. And so you can see there just what we've seen with the IF frequency on the left there, and you can see the local oscillator right in the middle, and I've tried to get those cursor lines on there, and you see we've got about 27 dBs of separation between the two. Now, if you look at it in the time domain, that's what it looks like. So you can see, even if you looked at that first, you know, there's a lot of harmonics in that. Now, this is the other mixer, the more recent one, which was built to exactly the same specifications as the one you've just seen, plus the Diplexer. Let me just go back a bit. That was the mixer on its own. That is the mixer with the Diplexer. Wow, it's night and day. Notice on the left, the IF signal, that there's a bit of loss because we're down a little bit from that E line. But look and try and find the local oscillator signal. It's completely gone. It's disappeared into the noise floor. So that is quite impressive. And all those other harmonics and things are well down. So that's really very good indeed. Now, the next one just shows you the loss, the difference from the output of the IF of the mixer on its own compared with the output of the mixer plus the Diplexer. And so we've got a loss. I mean, it's saying there 2.8 dBs. I wouldn't get too excited about these dB values. It's not the most precise thing in the world. As I said, it's not a spectrum analyzer here, but it gives us an idea. And I think when I did the test in the last video, it was just under 2 dBs, was what, 1.7 or something loss. So it's somewhere in that ballpark figure. So there's a little bit of loss, but look what you gain. You know, an awful lot of filtering action there. And of course, not just the filtering, as we saw last time, that wideband 50 ohms termination. And if we do the measurement of the level of local oscillator attenuation compared to the IF signal, instead of 27 dBs, we get 45. So, I mean, that's excellent, absolutely excellent. And if you looked at it in the time domain, you'd get that. And that would tell you instantly that that's a pretty clean signal. And indeed it is. Okay, so I wanted to just put these next to one another so you could see. So this is at the top, the original mixer on its own. And this below is the mixer with the Diplexer. And I mean, there's, you know, what can you say, really? I mean, that on its own, for me, is why I build Diplexers. But I did just want to address quickly one point, because I was curious, and I'm sure some of you are as well. This issue of, well, what about just sticking a filter on it? Because that's a fair point. And actually, it's interesting. So that's exactly what I did. So what you're seeing here is you're seeing the top chart is the mixer with a bandpass filter. So this is the old mixer with a 20 meter bandpass filter, which was close enough to the IF to get away with, compared to at the bottom the mixer with the Diplexer. And there's not a lot to choose between them, really. And in truth, the top one, the mixer with the band pass filter on the IF port, actually does a slightly better job of attenuating some of those harmonics. There's not a lot in it. It has slightly more loss, you'll see. Not a lot, but a little bit. But actually, this just underscores to me how remarkable the Diplexer is, because what we're comparing here is the proper LC bandpass filter with my little Diplexer. And you see that it pretty much does exactly the same job, pretty much as well, but as we found out last time, the bandpass filter is great at filtering, but is absolutely rubbish at giving a wideband 50 ohms termination. It's only as good as the very narrow bandwidth of the filter. Whereas our Diplexer is doing pretty much everything the bandpass filter is doing with slightly less loss and giving us a wideband 50 ohms termination. So, folks, I mean, you know, that's why I build Diplexers, really. Now, could you do the same thing in other ways? Yes, of course. Of course you could. Does the Diplexer do anything unique? No. You could do it, and you could just build a mixer like I did and put a bandpass filter on it, but then you'd also have to solder in a 51 ohm resistor to ground, or put a pi attenuator in to address that 50 ohms termination issue. And again, that's going to incur more losses, but also it's going to take up more space. And it's really nice for once, as somebody who has to build radios in bread bins because they're so big, it's really nice for me to build something that's actually compact and does quite a lot, you know, in not a lot of real estate on the board. I'm pleased with that, and certainly my Diplexer will be staying. Another way, second way, you can have a look at the output of your mixer in the frequency domain is to use one of these little things, a tinySA, Tiny Spectrum Analyzer. And yes, it's not as good as a real full-size spectrum analyzer, clearly, but it's not bad, and it gives you some indication of the different signal strengths that you can see. I've put some markers here. So marker number 1 is our IF frequency, and marker number 2 is the local oscillator, and we've got 23 dBs or something like that of a separation between the two of them. So this is the old mixer on its own, but I'll show you what it looks like when I connect in the new mixer with the Diplexer. And so now this is the new mixer with the Diplexer, and you can see the difference that makes. So you've got 10, 20, 30, 40 odd dBs there of difference between the strengths of those two signals, which is what we were seeing on the oscilloscope. And thirdly and finally, the third way I'm going to suggest you can view your mixer output in the frequency domain is same thing, SIGGEN mixer. Use one of these. So this is an SDR Play. This is an RSP2. I think they've been discontinued now, but this is the one with the 3 different RF inputs. But you can get different ones. I think the RSP1A is about £100 or something. So it's a little software-defined radio, but fantastic. Works as a general purpose receiver and so much more. And I'll show you what in just a second, because I'm going to need now to do some capturing on the screen, because I want to show you the software that I'm actually running on the computer with this. Right, well, this is the software which I'm running on the computer. So this is the RSP Spectrum Analyzer program. So it's free Windows software available on the SDR Play website, and it's terrific. It simulates, of course, a spectrum analyzer. There's all kinds of things you can do and markers, whatever. I'm not really bothering with too much at the minute, just to say I'm hovering over here and you can kind of see. So that's the IF frequency here. Doing a sweep from 0 to DC to 50 megs as before. That's the RF, and the local oscillator is here. This is the old mixer, and you can see and you can measure, as you could do with the tinySA, the amount of attenuation of the local oscillator signal, and you can tweak the controls and make it go up and down and get it to look the way you want it to look. But actually, if just for completeness sake, I'll show you what it looks like with the new one and the Diplexer. Okay, so I've swapped the controls over. So now this is what it looks like with the new mixer and the Diplexer, and you'll see, yeah, so we're up there about minus 29, and down here, yeah, so over 40 dBs of attenuation. So that's broadly in line with what we were seeing with the other two methods as well. And this is a really great method, actually. And where this is really good, in fact better than the Oscilloscope FFT method, is when it comes to building a balanced modulator, when you're trying to get a much finer resolution and get down to really low 5 kilohertz sweeps and below even, then that's where this is great. You won't be able to do that with the FTT thing, certainly not on my oscilloscope, and you won't be able to do it on the tinySA because it won't go in to that resolution. But you can on here. Yeah, it's a worthwhile investment. I'm not don't have shares in SDR Player or anything, but it's one of those things I bought, and I've always been pleased that I bought one, and I've used it far more than I ever thought that I ever would. But mainly for testing. So there we have it. So 3 different ways that you can test your mixer. Well, really the final thing to say is, obviously I have been testing my mixer or mixers with a signal generator. Now in reality, when I build a transceiver, I'm not going to hook it up to the signal generator. So that's something else you need to consider. Now if you're going to use something like an Arduino with an SI5351 phase lock loop module, which is what I tend to put in virtually all of mine, then what you need to do is, once you've worked out what the appropriate drive level is by using your SIGGEN or whatever, you need to kind of then try and get your output from your SI5351 to be as close to that as you can. And the way I did that is, once I knew what the output was and what that looked like on the scope, I connected the SI5351 in and tried to mess around with it. Now, to do this, what's really helpful if you've got some kind of stepped attenuator, which I haven't yet, which I need to get. But what I do have is a little set of these little separate attenuators that you can stack in series and build up anything from 1 dB to about 30 dBs of attenuation, and you can just keep swapping them until you see the right level of drive, basically. So once you've recreated what you had on the SIGGEN, you can be pretty sure that that's going to work then. So when you actually swap the SIGGEN out and put your SI5351 in, hopefully you'll have the right drive. Now, there's 2 parameters here. One, you can set the drive in software. You can set it to 2, 4, 6 or 8 milliamps. Now I wanted an excuse to put a pi attenuator on the LO port for all the reasons I've said before about wideband 50 ohms matching. So what I ended up doing was setting the drive quite low, actually. I set the drive to 4 milliamps in the software, and I worked out I needed, by stacking these together, 5 dBs of attenuation on top of that. So that's what I did. So in my code, I set the local oscillator port 0, as it is on mine, to the 4 milliamp setting, and then I messed around with these and ascertained that I need 5 dB. So what I will now do, now I know that, on back to my little board here, this bit over here, where we've just got a wire, that is where I'm going to build a 5 dB pi attenuator. And I'll know then that when I hook the SI5351 up into that I'm going to get the right amount of local oscillator drive. So yeah, so and that'll be the next job that I do. So thank you very much for watching. Again, in the immortal words of Charlie Morris, I am not an expert, but I hope just showing you these few different ways will give you some ideas about how you can build your own mixers and test them and make sure that you're getting out what you want to see and what you can do about that. So until the next time, thank you very much. Stay safe. Bye bye. Take care.